So we're going to be comparing two types or two paradigms of programming languages. The one that you're used to is imperative, like C++ and Java and stuff like that. And that's going to be doing a lot of computation, which is changing stored values, which is called a side effect. So every time you use something in C++, creating variables, even for for loops and stuff like that, you have a lot of side effects that are going on. Now, when we talk about functional language basics, this is going to be a longer video because there's a lot of features, but one of the first ones in a functional language is that the programming style is based off of functions with arguments, meaning you really are not going to have a lot of side effects, meaning you're going to accept a value, do some computation with it, and then spit the sucker back out. And it's going to use as little variables or have very little side effect as much as possible because everything is built into a function. So in the example that I have for you, you have the C++ version of counting a value up from 1 to 100. This is what you're used to. But notice all the side effects, meaning you're using I, then we're incrementing I all the time. Matter of fact, we have an X variable in there, and then we have something else after that with using length with, but all the equal signs that you see in there, that's side effects. That's taking up memory. That's taking up a whole bunch of things. Whereas these two lines are doing the exact same thing. Now, I'm not saying this is pretty, by the way, because this is starting to get interesting. We have parentheses within parentheses, and by the way, that's a major thing about Scheme is parentheses within parentheses, so heads up. But it really is the simplicity of this, is that you are frankly doing the total of exactly the same thing. It's set up as a function for you. And that function just does a calculation and spits a value back out. That's it. It's going to keep the creation of variables down to a minimum, if at all. And its only job is to accept parameters, do the calculation, spit the sucker out. Same thing with this. This is going to multiply. Yes, it is 3 variables, but there's not the reassigning of things or anything else like that. It keeps it down to a minimum, but it still does the job. But again, this is application-wise. This is math-based. You know, you're not going to be running Grand Theft Auto off of this. You might be in C++, can't remember what it's made out of, Java or C++. But anyway, there's also just a different untangible feel to why you're going to be using this for an application compared to this. So you're going to have to get used to that as well. So here's another example, and this time it's using not Scheme, but Haskell. And I know you're like, what Haskell? I just want to show you the example. If you can believe this, this one line actually has a lot of functionality in it, and it does a lot of work behind the scenes to get us down to a final answer. In this one line of sum and then 1 to 5, there's actually 2 functions that are happening. In reality, it's 3, but I'll show you that in a second. So I'm going to start with a list first. 1 to 5, that is the actual syntax of creating and applying that syntax to create a list of 1 through 5. Scheme has something very similar. Sum, I think you know what that does. Once we apply it, it's going to add the plus to everything. And when we apply everything together, it's going to, well, try to add everything together to get our 15. So notice how there is a reduction eventually after we expand our application on each one of those functions to get to our final answer. This whole thing is a function, multiple functions that come up with a mathematical solution. Now, functional language in its purest form, notice it said purest form, which by the way, Scheme and many other functional languages aren't exactly pure anymore. In their purest form, they try to prohibit the side effects, because again, this is very different than what you and I are used to. Imperative, accepts a value, calculates, spit the sucker back out. Now, with that said, is that it's going to keep the memory changes down to a minimum 2, or if at all. Because again, it's giving you the response, you do something with that response. The other interesting part about it is called Referential Transparency. This is one you have any 2 expressions in the program that yield the same value each time they're invoked without side effects. Now also that means that once you've defined it, which we'll go over here in defining, which actually is a side effect, but when you define it or you're running it or something of that nature, then it's going to be already there. It doesn't need to copy itself. Again, all it does is accept the value, spit the sucker back out, and go from there. So that's actually really helpful in classes that you'll talk about later with AI and behavioral information, all that type of stuff. That you'll talk about a little bit more later on. But mathematically, frankly, this should make a lot of sense with our FG and again, stuff like that, is I'm replacing the f of x, which equals y, and then now you just substitute that f of x in. So here's our substitution that we have here. And that's just fine mathematically. That's exactly the same idea as what we would have in our functional programming languages, that once we've created a function in that language, it's going to operate exactly the same no matter where you place it and then use it throughout your program. Very similar to what we have here in imperative. I know we have equal signs in here, and that's fine. But again, if I have function A, I can replace it with the value, and then still it would be or variable, I said value, but it would still be used exactly the same as what it was before. That's our transparency. So we all like being lazy. We're programmers. Come on. So there's lazy in functional programming too. Here's an interesting part. This is an addition. But how would you like to say, have you ever created an application where you actually never used the function that you built in it? Yeah. But remember, when you're doing compiling and stuff like that, that actually takes up space in the memory, and we have a whole bunch of different issues with that. Lazy is one way of getting away from that, is that in functional programming languages, it's not really defined and used until we have to. Now again, in Scheme and a lot of other functional languages that we have, they're not as pure as maybe they should be. So we have a lazy or a delay keyword in Scheme that actually says, you know what, wait on this. Don't do the computation or anything else like that. Wait until we have to, which is actually called force. But this is a way of calling a function by need instead of by value or something like that. It's kind of neat, isn't it? That's another way of doing this. So what we have also, I'm going to show you the whole program here, and again to my, to your most right-hand side here is some of the answers of what it would spit out. But I want you to take a look at it. In the code that you see in front of you, there's nothing super tough, let's put it that way. I bet you can figure out what display does, I bet you know what define does, but I talked about force and delay already. But take a look at it real quick. What I want you to do is take a look, and I've basically tried to line up where the displays are and what their solutions would be. But take a look at the questions I have at the very bottom here and see if you can answer it. So I'm going to pause here, take a look at the question. It shouldn't be too hard. If it's just guess, most of the time you'll probably get it right. So see you in a minute. So what would have las return normally without the delay? Now be careful, I'm dyslexic. Las is the name of the function. Delay is a Scheme function to wait on the computation of that. Well, lazy without the delay would have given us the 1 plus 2, which is 3. I'm sure you figured that one out, so nothing crazy about that. But why did the line display force of las display what it did? So in here, we have this line right here. Force is just that. It says, okay, I know you're sitting there. That's the promise right there. It's meaning, hey, I'm ready to go if you need me. I'm going to force the issue, force it to calculate, and that's why it does a calculation and displays that calculation of 3.